And welcome back to Mr. Gregoris Math. I apologize for the vocal tones today. I'm getting over a little bit of sickness. We're taking a look at doing some derivation from first principles. So we have a function r of x, and it's a combination function, so it has a couple of different components. It has a linear component, and then it has a nonlinear rational component. And then we're finding the derivative of it from first principles. So to do this, first off, anytime we see the words first principles, that's a pretty big hint that we're going to have to just start right here. So we'll start off with the definition of first principles, which is the limit as h approaches 0 of r of x plus h minus r of x all over h. That looks a little bit like an n. And so once we've done that, we've got two function pieces. We've got one piece where we go into r of x and we use our input of x plus h. So that means every single time I see an x in r of x, I'm going to replace it with x plus h. So this is going to give me a second line that looks something like this. My yellow portion. My first term was x, so it's going to be x plus h. And then I'm going to subtract 1 over 3 times x plus h. So that is the first portion of my first principles set. Now the second portion, and I'll make sure to keep this subtraction sign isolated, is just going to be a carbon copy of the function itself. So it's going to be x minus 1 over 3x. And this is all over h. So from here, I've got to go and find a common denominator, because I'm dealing with rational components here, and I've got to try and add these rational components. But you know what? It actually probably makes a little bit of sense to simplify first, because I could go and make a common denominator of 3x plus h in the yellow, but if I expand my view a little bit, this x and this x are going to cancel out. So it might actually be easier to simplify partway through rather than just combining everything all at once. So I'm going to go ahead and do that simplification. So this is the limit as h approaches 0 of x plus h minus 1 over 3x plus h. This negative sign is going to make negative x, and that's going to make positive 1 over 3x. So these x's then are going to cancel, and I'm still left with all of that over h. Now my common denominator, oh sorry, this should be still 3x plus h in brackets. I apologize for that. So now my common denominator has to have a 3 component, it has to have an x plus h component, and it has to have an x component. So I'll need to multiply this fraction by x over x, and this fraction, h, by 3x plus hx over 3x plus hx. That way I can take all 3 of those terms and add them. So I'm going to need a little bit more room to do that. And I have to remember to keep my limit notation the entire way along. So this h portion right here, I'm going to give a common denominator that takes into account both of those. So it needs to have a 3. It also needs to have an x plus h because of that. And it also needs to have just an x term as well. So it's going to look a little bit frustrating off the start. That's the first term. Then with this term, I already have that 3 in the x plus h. But I do need to make sure that it also has an x term. So I'm going to multiply the top and bottom by x. And then over here, I've got this 1 plus 3x term. I'm going to write the x over here because I want to make sure that my denominator for all 3 of these fractions is the same. So I'm going to multiply this one by x plus h, and I have to multiply the numerator by x plus h as well too. And in this way, I now finally have a common denominator. So that common denominator is going to be 3x plus hx, or 3xx plus h. I'm not going to worry about expanding it just yet. But I am going to write just slightly differently here. So I'll write my denominator, 3x plus hx. And this divided by h, I'm going to write it as multiplied by 1 over h. Because when we divide fractions, we can multiply by the reciprocal. And I think it's totally fair to do that here. So it's going to neaten things up so that I don't have these like multiple lines of fractions. Now I've got to go ahead and expand. So I have h times 3x, so that's 3xh. And I have h times 3 times h times, this is also times x here, so 3x squared h. Then I have h times 3 times h times x. So that's 3h squared x. Oh, I better be careful here. It's just h3 times that. And then each time, so I'm going to have two terms. Each time I'm increasing the power of x by 1 or the power of h. Did I get that right? Yeah. So that's the first two terms. Then here I'm going to have minus 1x, because the negative is nice and easy. And then here I'm going to have plus 1x plus 1h. Feel like I maybe made a mistake there. I'm not entirely sure. I think I might have. We'll see how this all works out. I actually am going to go back and double check this. So this was h times 3, or 3h times x. 3hx, 3hx squared. Yep, that term's right. And then 3hx, or 3h squared x. Yep, that term's correct as well. You got to be careful, especially when you have multiple variables in multiple spots. So that expansion, I should have probably written the 3 in front because I felt uncomfortable with the h in front. But now I have some more things that will cancel. So I have negative x and positive x, and those cancel. And the nice part is, I noticed now, just like I should have noticed in almost every one of my indeterminate form limits, or first principle limits, I noticed I have an h in each term left in the numerator. That's going to allow me to cancel with the h in my denominator term. So that's going to make things kind of work out a little bit easier for me. Now I'm going to common factor out the h so that it's very obvious. So I'll common factor an h from each of the terms remaining. So h, 3x squared, plus 3hx plus 1, because I have 3 terms that contained h, that term had a 1. And then in my denominator, this is going to be 3x plus h times x, and I still have this h over here, so I'll just put an h down on the side. And hopefully we see that this h and these 3 h's are going to cancel like that from our common factor. And once I've canceled, I've eliminated my indeterminates. So now I can substitute in h equals 0. In doing so, this term will still be 3x squared. This term will be 3 times 0 times x, or 0. And this term will still be 1. In the denominator, I'll have 3 times x plus 0 times x. Well, that's 3x squared. So this is the derivative from first principles. I can simplify a little bit though. I notice I've got 3x squared over 3x squared. So I can write this as 1 plus 1 over 3x squared. And that would give me my derivative. Now, there is an interesting point here, and both of these are correct. So that's correct and that's correct. That one maybe looks a little bit simpler if we're substituting in values. But it is important to note that here, x cannot equal 0. So if x equals 0, my derivative doesn't have a real value. Over in my function, if x equals 0, that part would be okay. This part also wouldn't have a real value because there'd be a vertical asymptote. And remember, derivatives give slopes, and vertical asymptotes are straight up and down. So what's the slope going to be at straight up and down? Well, it's going to be a vertical line. And remember, vertical lines have slopes that are undefined. So that's the reason why we would expect to have this restriction in our derivative, because we have that restriction in our function. This is going to happen whenever you have asymptotes or cusps. Those are things where it kind of comes together at a point and reflects about. So I hope this video provided some clarity on a rather challenging first principles example. We got through a couple of strategies. I think a key point was simplifying before you start combining fractions made it perhaps a little bit easier. You'd had more terms and it might have been more challenging if you didn't simplify first. And then just making sure you're keeping track of any expansions as you work through. Because it's very easy to make a sign error, or it's very easy to make a power error as you're working through these. You just sometimes have to slow down, go back, double check that what you've done is right. It's worth it rather than waiting to the end and going, oh, I made a mistake somewhere else. So checking each line is a good idea. Don't forget to hit like, subscribe, ring that notification bell. Do check the description as I'm going to put a link to the push-up challenge in this video. Many of the teachers at our school are doing the push-up challenge for the Canadian Mental Health Association, and I'm a part of the team as well. And so I'll put a link there, and you're welcome to donate to myself. I'll also put Mr. Carruthers' link as well too, so that you can donate to Carruthers. But I will see that you've donated to Carruthers, and that'll only affect the difficulty of the questions on tests. Take care. We'll see you next time.